Probably thinking, right? All right, so modeling data regressions involving exponential functions. So follow along, okay? Page 21. Questions involving doubling time. Okay, so a certain strain of bacteria is being observed in a petri dish and is known to have a doubling time, very important for us, of 7.5 hours. If the initial population of bacteria is, right, initial population is 2550, determine the equation that would model this situation. Okay, so when you have something like this, I would say that you should have time in hours in this particular case and compared to the population. Okay. In this case, they give you the initial population, which means that when time is 0, we have our 2550, right? And so after 7.5 hours, right, 7.5 hours later, we will have doubled our initial population. That's what doubling time says, right? So this, if you multiply that by 2, it's 5100, right? You doubled it. Doubles, right? And then so this is where a lot of students, for some reason, they just want to double everything. So they think, oh, two times this, because 7.5 and another 7.5 is what? 15, right? So they think it's doubling, but it's not. You will see when we do another iteration, it will change. But really, you're doubling. When another 7.5 hours go by, you're going to double what you had previously. So that's 10,200, right? So that's what's happening here. Let's make sure we understand what's happening when it comes to time. We're adding 7.5 hours every time. We're not doubling there. The doubling is happening in the population, right? Let's do one more. Times 2, that's 20,400, right? After 22.5 hours. That's why I go one more. Just for you to see that this side is just going up by 7.5 every time, and this side is doubling. The population is doubling. And so this is what did you just make here? You made a table of values, right, guys? This is a table of values, right? So this is L1, this is L2. You know that this was going there, right? Like after a while, functions kind of are repetitive to a certain degree. But here, all we needed is that doubling time, and that helped us come up with it. And so we go stat, calc, and I need to figure out, I haven't done this in a while. Stat, calc, I think it's 0. Yeah. Exponential regression. I like you to do this though, because in this course, you notice we're doing so many regressions that it's nice for you to actually write down what kind of regression am I performing here. And population growth, guys, is a dead giveaway for exponential functions. Right? That's why we always talk about the world's population growing exponentially, right? It's exponential. So let's come up with it. I first need to enter everything, right? So, oh, I did already. Did my homework. Yeah, that's still there. So I'm just going to go stat, calc, exponential regression. Second 1, comma, second 2, comma. Alpha trace apparently is the shortcut, right? If you just want to stick to the other method, go for it. But this is 2550. No surprise there, right? We could have actually started with that already. And then it's 1.09. I'm going to go 68. I'm going to put 4 decimals in there. Even though 2 decimals would have been okay according to the province. And so that's there. Okay. And so I noticed that it's increasing, right? So does it ask for the, it doesn't. So population, well, population increases by 0.968 or 9.68% per what? Per? No. This tells you per unit, right? So per hour. What you just found is per hour. You know that it doubles every 7.5 hours, right? But this, what you just found here is, like when you look at that, this is the rate of increase, right, of 9.68% per hour. So just look at the question, you will know, right? There's one homework question that you'll see, it's per observation. Someone's observing, right, every so often. So then there would be this much percentage per observation. So don't let that throw you off. Anyways, what's the population after 36 hours? I'm glad you asked because I know how to figure that out, right? So after this, it's really, you know what? Watch out for when it comes to time. This is often going to say after 2 days, right? You know that it has to be converted to hours, right? So just make sure you read carefully. So let's go ahead and find an appropriate window. I'm going to graph this and see my windows. Wait, too much going on there. I'm going to clear everything else. Oh, and remember, you can use, if you'd like, as long as plot 1 is turned on, you can use Zoom 9, but only to get you started, right? And in this case, it's actually very good. Like you don't even need to change it a whole lot, except for we know that 36, right? This Zoom 9 will include up to 22.5 and your X here. So I'm just gonna change my window to like 50. I don't need to go negative 400 really. I'm just gonna go negative 10 or something like that. And my Y max, I'm gonna go to 50,000 or something like that. Why did you pick those numbers? I don't know, it's just instinct. I just pick numbers and then go with it. So now I can find second trace 1, X equal to 36, and that's 71,000. It's actually past, it's not even on my window. But sometimes the calculator still calculates it. Other times it will complain. I don't know. I didn't make this calculator, so it had nothing to do with it. So we know that it's 71,036.926, but we know that it's population, right? Which is approximately 71036 or 71037 bacteria. No problem. How long will it take for the population to reach 14,500? Y2 is equal to that. We're going to figure that out. Y2 is equal to 14,500. Just make sure you add units. If you don't want to give me a whole sentence, right? I'm okay with that as long as you give me units, right? 18.81 hours. And I could convert that to hours and minutes if I wanted to. Why don't we do that? In case I get crafty and I ask you for that on a test or quiz, right? 80612, right? It keeps going. So this is hours. So this would mean that I have 18 hours and I will figure out the minutes, right? I take 0.80612 and I multiply that by 60. That's 48 0.36 minutes, which is just 48 minutes, right? Approximately 48 minutes. So it'd be 18 hours, 48 minutes. If it's just time, like usually if it's just how long will it take, you just stick with hours or whatever, days, whatever. But if it does say state your answer to the near hours and nearest minute, then you would do that, okay? State one limitation of the equation in A. As is, right? As is, time and population increase indefinitely. Okay, indefinitely. This is not realistic, right? This can't be since there is limited space in the petri. You know what a petri dish is? A little petri dish, little round containers where in science or chemistry or biology you'd be doing experiments on it, right? So you put like, I don't know, in some labs they put some bacteria in there and just observe the growth. But they need to add some kind of catalyst, some kind of food to it, right? So that bacteria can feed off of it and grow. But there's limited space and food, right? And food. Do you remember carrying capacity from science? Right? Like population can only grow so much and then it will kind of just flatten because there's a limit. There's some factors that limit indefinite growth. So there is a bit of a limitation to that. You'd probably have to have a domain and range here to restrict that. And so this is sometimes asked of you, like, hey, why is this not realistic? And just make reference to that. A tree cannot grow indefinitely, right? Trees grow, but at some point they stop growing, right? Or they at least slow down in their growth, right? Significantly. If the maximum capacity of the petri dish is 95,000 bacteria, state the domain and range. So that is, if they give you some kind of limit, right, then use that for your, so we're gonna find what time that would be, like at what time would you reach that carrying capacity. So let's go ahead and find that. And I need to, my window needs to be changed, right? I'm gonna go to 100,000 or something like that. And my X value, I'm probably gonna increase that as well to, some of you already know, I'm gonna go 250 for now. Oop, that's overkill, but that's okay. So that's, no, sorry, I made a mistake. It's 95,000. There, let's try it again. It's way up there. That's more like it. Always question your answer, right? So that's 39.15 hours, right? So we know, therefore, that our domain is time, right? So we started from time 0 with our initial population all the way to that 39.15, right? That after that, bacteria won't grow anymore. And our range, would go, what's our range? That's our lowest Y value. 2,550 all the way to the 95,000, right? So there you have it. There's a restriction. You're putting restrictions on that curve you just graphed. And I didn't graph it, right? We didn't graph this, but that's okay. Let's do a half-life. I think I left the back empty for the graph, but I think you're okay graphing. You're really good at graphing, I must say. Must have had lots of practice. in grade 11. Question involving half-life. THC found in cannabis has a half-life of 1.3 days in frequent users after it is consumed. If the initial amount after consuming a cigarette is 25 nanograms, right? State the exponential equation that would model the level of THC in terms of time. Okay. So let's figure that one out. So I would do time in days, and that's what we're dealing with in this case. And we have THC level in nanograms, right? So we know that the initially we would have 25 nanograms. 1.3 days after, right? You would be down to half of that, 12.5. And then you add another 1.3, right? 1.3, add it. You add another 1.3, it's 2.6. And that's where students always think it's doubling. Like they see it's like, oh, 1.3, 2.6, it's always doubling on the left side. It's not, okay? And then half of that is 6.25. So you're halving, right? Divided by 2, divided by 2, because it's half-life, right? Decay. And then let's do one more. 3.9, right? If you add 1.3 days, you'd be half of that. So you just, that'd be 3.125. Okay. We slap that into L1, this into L2, stat, calc, exponential. Should I say this? If you see doubling time and half-life, it's exponential. Don't even try, don't try anything else. Don't try linear or anything like that. Okay, so let's go ahead and do that. Oh, I can probably just borrow one of the top lines here. And I have no surprises with the 25. 0.5867 to the power of x. Okay. I'm not asking you for that here, so let's go ahead and just state that. This is a decreasing function, right? Decreases by, and this is a little trickier, right? Students just want to go always the trail end, like it's 0.5867. Not true. You need to go 1 minus 0.5867, and then you'll find out. And that's 0.4133 or 41.33%. Okay, decreases by 41.33% per what? What's our time? It's per day. Per day. So remember, if it's a decreasing function, you go 1 minus, right? I want to highlight that part, right? 1 minus that. If it's a increasing, then just take whatever is trailing the 1. That's easier, right? Okay. How long would it take for the THC level to be 5 nanograms? So that's y2 is equal to 5 second trace 5. I want to see if it's what the graph looks like. My window needs to be severely adjusted. Did you try Zoom 9? There you go. For exponential, actually will work quite well for you most of the time. I'm just gonna go 20 here, -5, 30. There we go. So y2 is equal to 5. Graph it, and let's figure this one out. X is equal to 3.02 days. If having a THC level of 2.5 nanograms or above is considered impaired driving, how long would an individual have to wait before driving? Well, we'll figure that out. So we go 2.5. 4.32. This must not be a very realistic. Nobody be driving, right? Yeah, that's probably hours. I have a feeling that I probably got that wrong. It's probably hours. But hey, it's more about the process, right? Limitation of the equation in A. What would you say is a limitation to this function? Do you think that the amount of THC in your body will at some point be 0? Yeah, if you wait long enough. But this equation never touches. Like this is saying that you never really get to 0. That's where you have to understand that an exponential never touches the x-axis. So that's the problem with this particular. So I will say this. Exponential functions never touch the x-axis. In other words, x is never equal to 0. Sorry, y is never equal to 0. However, the THC level in your body will at some point be 0. So there's a limitation to that, to this. It can only do so much, but not entirely. And that's that. And when I assigned some of these questions, I'm going to stop here. I forgot that one of the questions involved what we just learned today. And this is going to be this is going to be guaranteed on a test, either half-life or doubling time. So before you pack, I will ask you to consider the following homework questions. So on page, let me just go find that real quick. Page 18 and 19. Page 18 and 19 in the notes. Graph, please, if you can, as well. Plus, if you go past this page that we just did, there's a bunch of questions. So write this down first, okay? Very important that you try that. It's not that difficult if you just know what needs to be done, right? If you know what needs to be done, oh, doubling time, boom, I know what I need to do with that. Oh, half-life, I know what I need to do with that. I know what happens on the left, I know what happens on the right. But there are questions on page 25 and on that do the same thing. They ask you that same question. And then this should not take you by surprise, guys. If you're ever given a table like this, L1 and L2, you just type it in. Like there's no need to generate the table of values, right? So I would expect you to know how to work that as well. Yesterday was, let me just tell you here. It started before that, the 1819. So all those questions there. So pages 12 to 17. And I worked them all out, guys. I posted all those keys. So if you want to practice that, you go for it. Also, pages 12 to 17, right? That's what we did before today, right? So be confident with that because we are gonna start logarithmic functions. Like it's still part of this unit. You're like, log a what, right? Don't be too scared, but basically we just learned about these two here, exponential. Now we're gonna learn about these two. They kind of look the same, but they have different properties, okay? So don't fall asleep.